Yeah, for the last 4 class we were discussing about pericyclic reactions. So, in the pericyclic reactions we were talking about the one of the important class, that is your sigmatropic reaction. So, what we said that we can subdivide your sigmatropic reactions into two main class. One, we said it can be 1 comma n shift, or it can be your n comma m shift. So, in 1 comma n shift we said that it can be a residue shift, it can be your hydrogen or your carbon. So, we discussed hydrogen shift as well as we discussed carbon shift. In case of hydrogen shift, what we said that it depends upon the conditions in which you are using this reaction. For example, if I heat this reaction, okay, it undergoes a suprafacial as well as it can undergo suprafacial or intrafacial. So, Woodward you can use your Woodward-Hoffmann rule, and you can say that if it is a 4N system, if it is heating, you end up with your intrafacial. If it is a light, then you end up with your suprafacial. If it is a 4N plus 2 system, we said it will be suprafacial as well as intrafacial, other way round. So, that is what we discussed when it is for hydrogen shift. When we slowly studied 1,3, 1,5 and 1,7 in the case of hydrogen shift. Then we move towards your carbon shift. If it is your carbon is sort of not chiral, then you said that if it is just a methyl, it just obey like your hydrogen. If it is 4N, you will end up with an intrafacial. If it is light, it is suprafacial. Then if it is a 4N plus 2, it will be suprafacial and intrafacial, just like your hydrogen. But when you take about a chiral carbon, then things slowly you have to include one more phenomena, that is your inversion, or it can be retention. So, then we said slightly the rule, it can be intrafacial plus inversion, and it can be suprafacial or retention. This combination you see lot, 4N plus 2, then it will be suprafacial retention and intrafacial inversion. That is what we studied. See, only there was exceptional cases in case of 1,3 hydrogen shift. Both if you heat as well as you shine light, you do not get any reactions, right. We studied the reason for that, because what happens once you shine light or when you heat, you basically, since your hydrogen is very small, okay, it cannot make a binding. So, it is geometrically disfavored as well as you are seen like orbitally it is also not unfavored. So, 1,3 does not happen, 1,3 hydrogen shift does not happen in heating as well as light. So, that is what we understood in case of 1,3 hydrogen shift. In case of 1,3 hydrogen shift, you do not see any reaction. Okay. So, once we go for carbon, same way in 1,3 methyl shift, that is only one case where you see suprafacial inversion. Okay. 1,3 methyl shift, you can observe suprafacial inversion. Okay, these are the exceptional which we saw for that rule. Then we went to n comma m shift, which is nothing but movement of your sigma bond across your pi system. There we discussed, we said we will be discussing more on 2 comma 3 as well as 3 comma 3, right. In 2,3 we studied basically some important reactions. First we studied Wittig reaction, then we studied Stevens, then Somlet Asser, then we slowly went to our Meisenheimer. Okay. So, that part we studied in 2,3. In 3,3 we said that we will studying two important reactions. One is your Cope. We said we will study about Cope rearrangement. So, what we studied in Cope basically, we said that it is a 3,3 sigmatropic shift. Then we studied its stereochemistry, and we said that in the transition state, if it is an equatorial, the methyl, okay, that will be your most desirable product than your axial one. Then we said that the interconversion of your Cope can be increased by making your ring strain, where we talked about your bulvelin and everything. Then after that we said we studied a variant of Cope, that is your oxy-Cope, and we studied aza-Cope. In oxy-Cope, what we did is that we said that if we can make an enolate ion, then the rate of the reaction is increased. So, that is how we covered it. So, there is one more reaction which we have to study, which is your Claisen. Okay. So, today class we will be discussing on Claisen rearrangement, right. So, we studied 1, n shift, and then we studied n, m shift. We just moved across all these reactions, and today we will be studying our last one on sigmatropic reaction, that is your Claisen rearrangement. So, we will get into Claisen rearrangement. See, I have taken a sort of allyl ether. Okay. If I heat this, okay, I can number this 1, 2, 3, 1, 2, 3. Okay. So, I can move across just like your Cope. You end up with your okay. This is nothing but your gamma delta unsaturated aldehyde. This you can call as 3,3 sigmatropic shift. Fine. How to make this starting material, this allyl ether? Any idea?
That allyl aldehyde on treatment with vinyl -m.
Yeah, that you can do, or normally how people do that, you take your allyl alcohol, okay, and this is like famous method. You take your allyl ethyl, then you yes, because like simple systems, 1, 2, I need one more carbon here, OET, C8. So, this type of systems you can think of. Oh, sorry, I have not taken I have taken vinyl alcohol, right. Can take your allyl alcohol plus. So, this in mercury salt you end up with this product. right. And then you just warm the reaction, you get your Claisen, which is you end up with your unsaturated aldehyde. Fine. This is your Claisen rearrangement. Now, in Claisen rearrangement, the interesting fact is that, for example, I am taking methyl. Okay. I have now a system like this. Okay. Now, I say I do Claisen. So, do you think like how much product, how many products I can get? Any idea?
Two products.
You get?
Two products.
What are they? Yes, you can get E and Z, right. So, I can write this two products. So, first you number it 1, 2, 3 and you can write 1, 2, 3. So, one of my products will be, I can think of writing with a methyl here and with an hydrogen. Another product I can think about is with my methyl, other way around. Right. So, I can write E as well as I can think of getting Z, right. I can get an unsaturated aldehyde if I take a methyl substituent. If you see this product ratio, okay, there will be some selectivity. Okay. You can feel that E has been formed more compared to Z. Basically, in this case having a methyl, it is more like 60% to 40. So, you have some selectivity across your product. Fine. Any idea why it happens like that? Why it gives selectivity across one over the other?
Claisen goes through 6 cyclic transition state. So,
Yeah.
methyl will be
In one, very good. So, one will be in one case you will get in equatorial. Okay. Shall we draw the transition state? If I say one case, get this, and so my methyl, it is like pseudo equatorial, okay, hydrogen. In another case, if I draw, I can draw in other way around. Good. Then I can have my hydrogen and I can have my methyl, right. I can draw in two ways the transition state. This will, if I draw from here, I will get a product CH3 because it is hydrogen here, aldehyde. If I draw from here, I might get CH3. And then aldehyde. So, I get my E. If I draw from here, I get my Z. Okay. So, you can see that in one case it is like an, you can say it is a pseudo equatorial, but it is more like an equatorial portion, pseudo equatorial. In another case it is proper axial. So, you know that in cyclic transition state you want your methyl group to be favored to be in equatorial position. So, you get then E form more compared to a Z, clear. Okay. That is very important of your Claisen. So, this can be again the whole concept can be validated or verified more is that, for example, if I take a this type of substituent where I have like r prime, if I have both, okay, then what happens? Then I can write in both the cases I can write this, I can write r prime r here. So, I can get this two product, right. If my r prime and r, okay, if I make one as methyl, another as ethyl, then you can see that the ratio of this product, okay, now it becomes 90 percentage. In this case it is 10 percentage, because now you get 1 to diaxial interaction, which so it does not move towards, it will move towards more equatorial. This 1 to diaxial interaction makes it less, no, it is unfavored. So, you get this more. If I increase it to propyl and methyl, then it becomes 98 percentage and 2. Okay. So, that tells that yes, this goes to the cyclic transition state and it wants to prefer this equatorial position, just like your Cope rearrangement. In Cope also you have seen that cyclic transition state, it prefers to be in equatorial than in the axial. Clear? That's so that's we call as olefin selectivity in Claisen. Another important thing in Claisen which you come across is your exocyclic olefin and endocyclic olefins. Okay. For example, I have a I take a tertiary butyl, okay. I have a double bond system. Okay, I have taken the system which is exocyclic, right. Taken an exocyclic olefin. Now, what do you think? How many products you can think about? So, it is first a Claisen. So, I can write 1, 2, 3, 1, 2, 3. Okay. So, again it gives, you can think about two products. Okay. If you write in this way, you have your tertiary butyl. I can write in one way is like this product, OET, right. I can get this product. So, you can push this back, you can get it here. So, I can this product. Okay. Another way I can write this is tertiary butyl, you can get in other way around, because this you can think of getting it up. So, in exocyclic you can think of this two type of products. Okay. So, I can say the yield in this case it is 52 percentage, in this case it is 48 percentage. So, there is not much selectivity, you get both the products. Okay. We will find out the reason when we talk about the endocyclic, then you know the reason why it is happening, why you are getting both equally. Okay. There is no selectivity across the products. The same example if I take for endocyclic. For example, I take an endocyclic system now, like endocyclic olefin. Oh. have a double bond, okay, with an, okay, I will just give a space, sorry, just do not rub it, just for you. I take an olefin like this, okay, more like an endocyclic. Now, if you just eat this, I get basically only one major product. This I get around only 87%. Hmm? Yeah, sorry, I missed my tertiary butyl. Fine. So, you can do your, so you know how to do Claisen. So, why it happens like that? Again you can get back to its transition state, cyclic, that type of transition state, see whether you can visualize it properly. See, if I draw for this tertiary butyl. Ethyl. See, it will be only on one side it will be favored, okay. Since you have a tertiary butyl, the other side it is not favored, okay, because of your double bond. Because of your double bond, the one side it is much favored than coming down, fine. But in the earlier case,
the bond will be formation from below the plane.
yeah. So, in the earlier case it will be on the both the side in exocyclic, you do not have that constraint when you talk about exocyclic. So, that is why it can be formed below as well as above, you get equally, but in the case of endocyclic it will be only on the one side. So, you get 87%, that is your selectivity. So, most of the time people ask in Claisen, okay, if you take an exocyclic, what type of selectivity you are talking about, when you take an endocyclic, what type of products you are getting, that then people will ask about more olefin also, okay, like which will be dominating, whether E or Z. These two things you should know about Claisen reagent. Clear? Okay. See, Claisen is good in one sense, like
Intermediate.
yeah.
I want to look at.
Okay. I want to see.
I have to draw that.
Oh, you want to draw it? Oh, okay, fine. I will give you, yeah. So, look at this. So, you have a tertiary butyl, then you have this, and you have an interaction. Even if you see the models, if you can make it, will be nice to see this type of structures. Fine. Okay. See, in Claisen we have lot of variants, right? You have studied lot of variant in Claisen rearrangement, like any modified Claisen, variants in Claisen, you remember. There are a lot of variants in Claisen rearrangement. Johnson Claisen, okay, you have studied Claisen Ireland, lot of this are there. So, we will discuss that part, okay. So, first we will say we will take Johnson Claisen rearrangement. Because they have very good synthetic utility. Johnson Claisen. So, what it says is basically again what you do, you you take an allyl alcohol, right. In Johnson Claisen you can have your orthoesters, like you can make this. Nowadays it commercially available also. Just in H plus you end up your O, this is your oxygen. Okay. You end up this substrate. Okay. Now you can do a Claisen, right, across this. If you heat this, you know how to number this 1, 2, 3, 1, 2. Just you heat this, you undergoes nice 3,3, which is your Claisen. See what you got in your regular Claisen rearrangement, just Claisen, you got your gamma delta unsaturated aldehyde, right. In this case you end up with your gamma delta unsaturated ester, and from this you can do many synthetic utility. There are many reactions which we will do in the problems. Okay. When we do problems, then we come across like you can use lot of natural product synthesis using this type of reactions. Johnson Claisen, that is why it is Johnson Claisen. Finish. This just goes by warming, okay, even does not need to heat too much, just by warming it goes. Then another is your this salt S-monos Claisen rearrangement. Another important variant, just like your Johnson, just like Johnson Claisen. You take an allyl alcohol, instead of making an orthoester, can have like this N-dimethyl. You have studied this osmosis salt, right. So, type of reaction, you take this. Now, what happens? You react, you end up with can have your dimethyl here, which is ready for good precursor for your Claisen. Now, if you warm it, it undergoes a nice 3,3, 1, 2, 3, 1, 2, 3. So, you can do with amine and everything. So, you end up with your nice amides type of system. Okay. In this system you can gamma delta unsaturated type of amides you can think of making from here. Okay. Your Claisen, you thought about an aldehyde. Johnson Claisen, you can think about ester. In this Exmolar Claisen, you can think about amides. Okay. Then there is another good is that, so it's Claisen has a very good variance, okay, that you should remember. Then there is another, like we call it as Ireland Claisen rearrangement. Okay, in Ireland Claisen is just similar like that. You take your same allyl alcohol, okay. What is this? Hmm? Yeah. So forget. Okay. So you just treat it with an amine, okay, in any base. This reactions all go very fast, like and with a very good yield. You get this. Fine. And yeah, this is methyl carbonyl O carbonyl methyl. Yeah, this is like an ester of your methyl. No? Yeah, this is little bit that needs a CS2 in between. Anhydrides of yeah. This is anhydride, acetic anhydride. CS3 C double bond O C, right? Yes. So you put it in base, you just open up and you get your product. Sorry, this is just an anhydride. I just confused. Then you treat it with your this base. So yeah, 3. You get this. Now this is ready for your. This is your precursor for your Claisen. Okay. You get this again. Number 1, 2, 3, 1, 2, 3. So you can end up OSIR3. Then if you want, you can hydrolyze this and okay. In this case, you end up with a gamma delta unsaturated acid. So you have seen making aldehyde, you have seen making ester, amide, and now acid. Fine. This is your Ireland Claisen rearrangement. There are a lot. You have Overman Claisen. You have a lot of Claisen rearrangement. I have just taken the specific ones and I am just teaching you. N numbers are there. Okay. There is a type of Claisen rearrangement which we call as Carroll rearrangement. It's a proper Claisen. Okay. Call them as Carroll rearrangement, which comes under Claisen. Same way you take an allyl alcohol. Most of the case your allyl alcohol is your substrate. Okay. You have your above ketene system. Then you just add them, you end up with your it becomes a nice now for Claisen, right. So, you can write now 1, 2, 3, 1, 2, 3. It gets good for your Claisen now. Okay, you get this product with an acid, but your alpha substituent. Okay. Gamma delta unsaturated acid, but with the substituent in the alpha portion. This is your Carroll rearrangement. Okay. Comes under Claisen. It is a proper 3,3 sigmatropic. Okay, so far the Claisen we were discussing is more about your aliphatic type of systems, and you know that Claisen, aromatic Claisen is well common. Okay, lot of aromatic Claisens are there. We will see one example of aromatic Claisen rearrangement. So, we will do the aromatic Claisen rearrangement. What's your best system? Yeah. Yeah, we are. Get this. This on eating. Okay, you can write the Claisen for this 1, 2, 3 and 1, 2 and 3, right. So, I can shift this to this and this to this, right. So, ending up me ketone with a nitrogen. Then you know it gets aromatized. Give me okay. This is your aromatic Claisen rearrangement, right. Okay, these are more about your Claisen, okay, the different variants of your Claisen. So, we have taken Claisen, we said that it can be a 3,3 just by warming you get it, and we just moved to the olefin selectivity, and we said that yes, you can see olefin selectivity. Then we said that exocyclic gives both the products. In endocyclic it is only one you get as a measure. And then we studied variants in Claisen, we studied Johnson Claisen, we studied Ireland, right, and aromatic Claisen, Carroll rearrangements like that, fine. This comes under your Claisen rearrangement. So, this is more about your 3,3. We will see some other 3,3 and some other rearrangements, like few examples. Okay. Do you remember your Fischer-Indol synthesis? So, what type of rearrangement it is? Fischer-Indol synthesis. There is a type of sigmatropic rearrangement happens, right, in Fischer-Indol. What it is? Can you remember what rearrangement it is? It is 2,3 or 4, yeah, what rearrangement it is? Yeah, it is again 3,3. Okay. So, modified Claisen, instead of oxygen you will have nitrogens. Okay. Yeah, that is how you remember it. Okay. It just comes under the class of Claisen. If you remember like that, then you think it is a 3,3 directly you can say. We will just see that. The system normally you make this in Fischer-Indol, right, you get this. This you know it undergoes, it is always tautomerized, right. So, you can have a tautomerize to give you okay. Now, if you number it, it will be good for your Claisen, right. 1, 2, 3, I can write here 1, 2 and 3. If you want, I can push these arrows and you get this. So, it is a proper, just treating it gets in 3, 3 sigmatropic shift. Yes. Okay, you get this. This then you in several steps, in 2 or 3 steps, you know that this will end up with your indole. can nicely make indole of this. Okay, but this it's a proper sigmatropic reaction of 3,3 Fischer indole. Okay. Yeah. Now I will give you an example. Just try and let me know what sigmatropic shift it is. Okay. Take this example. Just I put a sodium methoxide. Okay. So, you know you can generate a carbon anion here, right. So, phenyl generate a carbon anion nicely there. Now, tell me what it will be. What shift you can expect out of this? Yeah, just the first thing is just you label number them, that is more important when you do. So, 1, okay, 2, 3, 4, I can say 1, 2, 3, 4. In this case it is 1, 2, 3, 4 and 5, right. So, you want to break your 1 bond and you want to form it, right. So, yeah. So, I can break this. So, initially if you want to move things, okay, I can move, yeah, nitrogen. So, what shift is, so what product is this, what shift it is? Sigmatropic 3,3 or what it is? So, it is a 4,5 sigmatropic shift, okay, because your new bond is formed between 4 and J, that is your N, M, right. Yeah, you get this product 4,5 sigmatropic shift. So, you can see 2,
here total electron number is 9.
Yeah.
But this is odd number. 4n plus 2 or 4n plus 1 is not.
Yeah. So, it is on heating, nah?
Yes, sir. But I am taking the. I am considering the Woodward-Hoffmann rule. It is telling for even number of.
So, you have 2, 4, 6, 8 and you have this 2. No, you have not taken the carbon anion 2 electrons. That you have to
3 pi 1,
yeah.
sigma 1 and 1 lone pair.
So, you have to consider this one, right? Yeah. So, you have to consider that, then it works fine. Do not leave that carbon anion because there is 2 electrons there, lone pair of electron. Then you have studied this Claisen, you have studied one very interesting Claisen, that is
This is very good example.
Yeah, last one. So, this is what do you expect in this? Huh? Yeah, if I do heat it, okay. So, what sigmatropic shift you are expecting? Yeah, just 3, 5 or can I write 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. Is it just possible because I am going to move this. Yeah, you can get nice 5 comma 5 sigmatropic shift. In Claisen you can see that 5 comma 5 with 3 comma 5 also you will get, but this is a good example for your 5 comma 5 in Claisen. So I get I can get product like this, right, and this can aromatize very fast to give me right. You can get this. This is 5 comma 5 sigmatropic shift. It's an higher version of your Claisen, more like your Claisen, but higher version of your Claisen rearrangement. So, we will start doing once we finish this, then we will start doing the problems. So, in problems what happens if you have a very big molecule, okay, then the idea is that you have to identify that. I will say it is heating, then you have to identify whether you have a cope system in that big molecule, or you have a Claisen system, okay, or it can undergo 1 comma 3, or it can undergo other 2 comma 3 like Wittig or Stevens. So, you have to identify. So, what I will do, I will bring some natural products, okay. We will identify the systems, just sir, it will go cope, this system looks to be a Claisen, this system looks to Wittig, this looks to be 1 comma 7 suprafacial, like that, 1 comma 7 antefacial, fine. We will just work on that. Take this example, which is so. What is this molecule? Yeah. So, what do you expect in this if I heat this? Because it is more like an aromatic, yeah, you can get 9 comma 9 sigmatropic shift. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. So, yes, sir. Oh, sorry, sir.
Only heating is sufficient, I think.
Yeah.
Now it is okay.
Yeah, now it is. So, I just 1, 2, 3, 4, 5, 6, 7, 8, 9. Just take this and slightly warm it, undergoes very good 9, 9, okay, sigmatropic shift. So, what you get then? So, you it's a nice system to work on. So, now what happens? Yeah, it will aromatize. So, you see the product. That you get a very nice products. So, So, this is a 9,9 sigmatropic shift. Fine. Okay. So, we have seen that 5,5 and this is your 9,9. So, that is good. So, what we covered is that now we have seen sigmatropic. Okay. We know now how to work with your 1 comma n, we know now how to work with your n comma m, and we have seen Cope, Claisen, and now we have seen other things. What we will do is that like next class we will get into cyclo addition reactions, but meanwhile I will give you some problems also where we can see the cascade synthesis, how it can be identified, but we will start from this class cyclo addition reactions, right. Okay. So, sigmatropic. So, pericyclic reaction, the first class we have finished is sigmatropic. So, we will now go to the second class of reaction, that is your cyclo addition. Okay. We will take some 4 or 5 class, we discuss about that, then we will go to your electrocyclic, like that we will slowly move on. Fine. So, with this we will end our class today.